Hello and welcome. This is an overview of the Unit 4 assessment. Now, your questions are likely to have been randomized, so you would have to find the ones that you need help on by fast forward or rewinding this video. So most are conceptual from Unit 4. However, some are mathematical with some of the mole and gram conversions or law of conservation of mass. So I'll go through how to do all the math work as well. So the first one on mine is that ionic compounds that dissolve in water make the water conductive. This is a true statement. That means that we have free ions with positive and negative charges. It's mostly those negative charges that allow electricity to flow. So electricity is just the flow of electrons. So for this number 2, this is showing that a student has failed to zero out the scale and then tried to take a mass of something, and this would be making the value too high because you're not only taking the measurement of mass of your sample, but of the dish it is in. Which of the following substances will conduct electricity? Select all, apply for this number 3 here. Solid sodium chloride is not dissolved, so that means it is neutral as a solid compound. So its ions are not freed up yet because it would need to be dissolved. So solid sodium chloride will not conduct. Pure water shouldn't have any ions in it or metals. Tap water, on the other hand, perhaps conductive, but pure water, not conductive, no ions there. Table sugar, sugar is a molecule, and so molecules do not make ions when they dissolve. They stay in their molecular form, and so none of those first 3 will conduct. Solid iron is a metal. Metal is highly conductive because of C of electrons for metallic bonding. Sodium chloride dissolved in water is different than solid sodium chloride in that the ionic bonds are able to be disrupted by the water molecules, making positive and negative ions available, and electricity can flow. For number 4, we're talking about an experiment where a scientist is doing electrolysis of water, and so it explains that water is decomposing. So if you know your reaction types, that means that water is the only reactant, and it's breaking down into hydrogen and oxygen gas, its components. So if we put in 4 grams of water and make 0.44 grams of hydrogen gas, how much oxygen did we make? So here I'm going to pop out to do a little bit of math on the screen. So this is just law of conservation of mass, and so it might be helpful to draw out the reaction equation itself. So H2O with your arrow yields H2 and O2. I do know that I've made 4 grams of water, I've put in 4 grams of water as a reactant, and I've made 0.44 grams of hydrogen gas, and I'm wondering about how much oxygen. So in a perfect scenario with this experiment, following the law of conservation of mass, we know that we cannot create or destroy any matter. So all you would have to do is just subtract the 4 grams or the 0.44 grams by 4, and that would equal 3.56 grams of oxygen. Which of the following does not help us identify a substance? Well, the solubility does, the color and the conductivity does. Those are all substance or properties that we tested of substances in Unit 4. But if we mass a substance and have 10 grams of salt versus 10 grams of sugar, the 10 grams does not help us identify anything for a particular substance. Number 6 is balancing. So you would have a 6 for your coefficient in front of the potassium, a 1 or just nothing there for the nitrogen, and then a 2 for the potassium nitride. Number 7 is talking about another reaction where we'll have to do some simple mathematics for law of conservation of mass. So we have magnesium metal reacting with oxygen, forming magnesium oxide. Again, might be helpful for you to write up that whole equation to kind of visualize it. And so the scientist is going to put in 5 grams of magnesium and 2.5 grams of oxygen gas, and then make 6.3 grams of magnesium oxide. And so if you add for the 5 and the 2.5 together, you get 7.5, but that's not how much product we made, so there has to be some leftover reactant that did not react. And so we call that an unreacted portion. And in Chem 2, you'll learn lots more about that. So with this one, we have magnesium at the, I lost my numbers, there we go. The 5 grams and oxygen at 2.5 grams. So I'm going to add those up and get 7.5 grams of reactants. And then they said that they made 6.3 grams of product. And so 7.5 minus 6.3 means that we have 1.2 grams of the magnesium that has not reacted. The mass of 1.5 moles of table salt is another one where we have to do a little bit of mathematics. And so this is where that dimensional analysis comes in, or the railroad track method of multiplying and dividing. And this would be a moles to gram conversion. So I'm actually going to pop back out to Notability to do that math. And so for this one, we started with 1.5 moles of sodium chloride. We know that we have to cancel our units, so we should have 1 mole of sodium chloride on the bottom. And then our only conversion factor that we know in this next step that relates moles to grams is the molar mass off the periodic table. So I'm going to go to the periodic table, find the mass of sodium and chlorine, and add them together, and that is 58.44 grams per 1 mole of sodium chloride. So I'm going to multiply 1.5 times 58.44 and divide by 1, and I should get 87.66 grams of sodium chloride. All right, for number 9 on my copy, when an iron nail is placed in a beaker of water, it makes the water electrically conductive. No, it would have to have somehow leached into the water for that to happen. So the nail itself is conductive, but not the water. What type of compound is magnesium oxide? Well, that is even from like unit 2, so it's a metal and a nonmetal coming together, so that's an ionic compound. If it were covalent, it would be 2 molecules, two nonmetals, and it's not just a metallic bond because that oxygen is in there. For number 11, if we're looking at pure substances, we did the first big lab that spanned a few days in this unit. We have copper doing the flame tests with a blue-green flame and iron 3 chloride with a kind of sparking orange flame. So that would have had to have been from your observations of when we looked at our reactants and products, and mainly products of the lab where we reacted the iron nail with copper 2 chloride. This one for my number 12 was from number 4. It was kind of a virtual lab scenario that we gave you of when we heated sodium bicarbonate, baking soda, and changed it into sodium carbonate, CO2, carbon dioxide, and water. So we did look at the amounts and kind of looked at some sample data, analyzed it for getting to the law of conservation of mass. 13 is a balancing equation. Again, we're taking sodium chlorate and decomposing it into sodium chloride and oxygen. So that one is 2, 2, 3. The molar mass of table sugar, kind of a hefty molecule there, 12 carbons, 22 hydrogens, and 11 oxygens. You'd have to get the mass of carbon off the periodic table, 12.01, the mass of hydrogen, 1.01, the mass of oxygen, 16, and then multiply each of those values by their respective amounts, and you should get about 342.30 grams per mole. All you would need to solve for that one is your periodic table. 15 is just identifying different types of chemical reactions, looking at patterns. We even gave you this helpful, chart down here. So the iron nail dissolving, we identified that as a single replacement reaction. So the copper was booted out of the copper 2 chloride, and that left some iron 2 chloride being produced. Oh, sorry, lost my spot. When sodium metal combines with chlorine gas to produce sodium chloride, sorry, my dog's making noises, you have a synthesis reaction. So you're putting together substances to make one product. Again, steel wool burning is an example of synthesis because we're putting together iron and oxygen to make iron oxide. And then lastly, a double replacement reaction. These are always really simple to spot because you have 2 ionic compounds going in and 2 ionic compounds being formed. When we burned steel wool at the beginning of this unit, we noticed in the video that the mass went up. And so usually people think that, burning something is something that would make the product be lesser, but actually that is not true in that case. You're synthesizing a product and you're adding oxygen to the steel wool to increase its mass. For this one, we're looking at which pattern of reaction type where 2 different metal ions switch negative ions, and that's going to be, again, double replacement reaction. So double replacement showing up a few times. For this one, another balancing, a synthesis reaction where we've got aluminum and oxygen coming together to make aluminum oxide. So that balancing for this number 19 is 432. And we've got one more math one to work out together for this number 20 example. How many moles of water are there in 100 grams of water? So we're going to need the molar mass, and we're going to convert grams to moles in this example. So we're going to go to notability. Again, more dog noises, apologies. And we've got 100 grams of water. I need my molar mass of water from the periodic table because I need grams of water down here per 1 mole of water. Again, that is the molar mass. The only conversion factor we know so far to go from grams to moles or moles to grams. So I have 1 oxygen, 2 hydrogens. I'm going to add those values together, and I'm going to get 18.02 grams of water. So it's probably a molar mass that you'll end up memorizing eventually if you move forward with chemistry. So our grams cancel out, and we're going to take 100 multiplied by 1 divided by 18.02 and get about 5.55 moles of water. All right, last but not least, this example for my number 21 is just basically a definition of why or how our balanced equations represent the whole number mole ratios, and those are proportional to the coefficients in our balanced chemical equations. So we have to be able to convert in and out of moles into grams in the future. If you're moving forward with chemistry, we've got different conversions of going from moles to liters, and so many more different things we can do by using our whole number mole ratio coefficients. All right. Hopefully this was helpful. Come back with questions about your specific assessment, and we'll see